So if we run the t-test, let's look at our first research question. So whether or not having no soy meals produces higher sperm counts than if you had one soy meal per week. The syntax is t-test, the name of group 1 exactly equals the name of group 2, and then we need to say unpaired. Unpaired is telling stat to run an independent samples t-test. And what we can see here is we have 20 people per group, so a total of 40 people. The mean for our no soy group, the mean sperm count is 4.9867 units, whatever we're measuring this in. And if you have one soy meal per week, that drops to 4.61. So the difference in the means is 0.38. And this difference is calculated as the mean for no soy minus the mean for one soy. So 4.98 and a bit minus 4.61 and a bit. And this produces this value here. We can see the standard errors and the standard deviations. It's kind of interesting. We do want to look at the standard deviations because we were interested in the quality of variance. 5.08 and 4.67 are exceptionally close and are probably okay. We can see confidence intervals here. These are the confidence intervals around our means. So with 95% confidence, we can say that the sperm count for no soy meals is somewhere between 2.61 and 7.37. And for one soy meal a week, it's somewhere between 2.42 and 6.79. We can also get a confidence interval around the difference, which is down here. And we can say that with 95% confidence, the mean difference in sperm count between no soy and one soy meal is somewhere between negative 2.74 and 3.51. Now, if we think back to what the null hypothesis of a t-test is, it's that the mean DV for one group is the exact same as the mean DV for another. So if that was the case and I calculate the difference score would be 0. Now, the t-test output actually tells me this. Difference equals mean no soy minus mean of one soy. Then it says the null hypothesis is that the difference would equal 0. Now, if the 0 here is somewhere in my confidence interval, so in other words, if there is within 95% confidence a chance that the difference between my two groups could be 0, then I will have a non-significant t-test. And that's indeed what we see here, right? We have a negative through to a positive, which means that 0 has to be somewhere in that confidence interval. From our lower bound to our upper bound, we cross 0. Lo and behold, we get a t that is less than 1. It's on 38 degrees of freedom. And our p-value is non-significant. So I'm looking at the p-value on the far right, and the reason I'm doing this is because we're expecting a difference that is positive. So difference is greater than 0. And the reason why I know this is the difference that I want to be looking at is because we had the hypothesis that having no soy meals would produce a significantly greater sperm count than one soy meal. And we already know that if the mean of no soy is higher than the mean of one soy, which is the case we have here, then the difference is a positive score. The difference is above 0. So that's why I'm looking here. This is my one-tailed t-test when I'm expecting my group 1 to be higher than my group 2. And it's non-significant. My p-value is greater than 0.05. If I was expecting no soy to be less in its sperm count compared to one soy, I will look at my other t-test over here. And this in the middle is if I didn't expect any direction at all. So if you remember, I was saying that we are effectively cutting our 0.05 down the middle if we don't expect any direction. So we're making it much, much harder to find significance. And if you look here, the p-value for our two-tailed t-test is twice the size of our p-value for the direction that we're actually expecting. So this is suggesting that having no soy meals per week does not increase the amount of sperm that you'll have if you eat only one soy meal per week. There's no difference. Go ahead and have that one soy meal per week. But that's not the only question that we have. Let's look at no soy compared to 4. We start to see that the mean is dropping. So up here, having only 1 soy meal a week, we had a sperm count of 4.61 units. And for 4 soy meals per week, it's 4.11. It's starting to drop. Remember, though, that we didn't have a direction. So now we're looking here at our two-tailed t-test, and the p-value is still above 0.05. There's still no difference. We can also see that our t is 0.58. It's still on 38 degrees of freedom. Let's have a look at the last one. No soy compared to 7 soy meals. The sperm count has drastically dropped if you have 7 soy meals per week. It's down to 1.65. With 4 soy meals, it was 4.11, so we have a huge dropping off. We can now see that our confidence intervals don't include 0. Our t statistic is considerably large. We're still on 38 degrees of freedom. And our two-tailed is significant. Now let's say for a moment that we actually were expecting no soy meals to produce higher sperm counts than 7 soy meals, which, if you think about it, is not a logically silly idea given that we expected no soy would produce more sperm than 1 soy meal per week. If that was the case, I would look again over here and I would see that it is significant. Interestingly, this p-value is half the size of my two-tailed. It's more significant, and that's because we're lumping all of our 0.05 here, whereas we're cutting it in half here. If I look over at my other side, my one-tailed t-test for if no soy was less than 7 soy, what I notice is that the p-value is extremely close to 1. So it's extremely unlikely that I would get these means if no soy was actually a lower mean than 7. Now, I could have predicted that this would be non-significant, this would be significant, because my confidence intervals here are both above 0. If they're both below 0, then I would expect the reverse pattern to be true, where this would be significant and my higher would be non-significant. Now, I guess the next question then is there a problem with this approach? Is there a problem with running 3 t-tests? And the answer, quite simply, is yes, there is. There's actually quite a big problem. And that problem is that every time we've run that test, we've used a p-value of 0.05. But it's the same IV, right? It's still just the amount of soy meals you had per week. We're just comparing different levels. In this case, we're comparing no soy 3 times. What this means is, let's say we accidentally made an error in our data collection with no soy, every single one of those comparisons would carry over that error. And so we talk about this conceptually being an inflation of what we call type 1 error, which means you're much, much more likely to find a significant effect when no effect actually exists. So it's kind of like a false positive. A type 1 error is the equivalent of telling a man that he's pregnant, whereas a type 2 error would be, which is the opposite, it's a false negative, would be telling a very, very pregnant lady that she's not pregnant at all. So when you have multiple t-tests, you run the risk of a type 1 error. You risk telling a man that he's pregnant. And the reason for this is every time you're comparing multiple groups within the same IV, your 0.05, your definition of significance, actually starts inflating. And it gets larger and larger and larger. And so when you run 3 t-tests like this, you're actually comparing overall, you're comparing the number of soy meals effectively to a p-value of 0.15 when you add it all up. So we need to find a way of running these 3 tests without actually inflating our type 1 error, without actually using 0.05 3 times. We want to use it just once. We want one p-value to represent all 3 tests. So that's where ANOVA comes in.